5.3, let's look at some application problems. So every cross-section through the vertex of a paraboloid, so this is a paraboloid, is a parabola with the same focus. So a paraboloid is a three-dimensional version of a parabola. To see why this is important, imagine electromagnetic waves heading toward a parabolic dish and then reflecting off the dish onto the focus or the receiver of the dish. So the receiver is at the focus. Anything that hits the parabolic dish reflects directly onto the focus. And this is how things like flashlights with that concentrated light work, satellite dishes, things like that. Okay, let's go through this example. A satellite dish is to be constructed in the shape of a paraboloid. If the receiver placed at the focus is located 2 feet above the vertex of the dish, so here's the vertex, here's the focus, and the dish is to be 12 feet wide, how deep will the dish be? So we're trying to find this height right here. See the question mark? We've got 12 feet across here, we've got 2 feet here, we've got the vertex here. Now, when it's a real life question like this, if you need to create a graph in order to create the equation, like sketching a graph, put your vertex at 0, 0 and make your parabola go upward, because that is like the easiest thing to do, right? You can put it wherever you want, so you might as well situate it in a way that's easy. So you can't see that very well at this point. Because this is 12, that point will be at 6 comma y, and that y value is the number we don't know, the height, depth of the dish. And then this point will be at negative 6y. Okay, so let's start working on our equation. Since we're putting our vertex at 0, 0, all we need is x squared equals 4p times y for our equation, right? We just used the simple one. I've gotten used to the harder one, and I wanted to make it more complicated. Okay, so then we have 2 points we can choose from, and it really doesn't matter which point we use, because if we use negative 6 and we plug it in for x, we get negative 6 squared, which is positive 36. If we choose to use positive 6, then we square it and we get positive 36. So it does not matter which number we use. So we're going to plug that in. So we have 36 equals 4p times y. Now, I just realized we actually do know what p is, and we should plug that in too. So p is this distance right here, which is 2 feet, right? So 4 times 2, and then y is the number we don't know. So we have 36 equals 8y. Let's divide both sides by 8. So y equals 36 eighths, which reduces to, dun, 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 I can't do that in my head, can I? Let's see, divide both by 2. So 18 fourths, so 9 halves. Oh, that's easy, it's 4.5. Cool, we found the height of our satellite dish. All right, let's do a very similar but slightly different problem. Example 7. Cross-section of a design for a travel-sized solar fire starter is shown below. The sun's rays reflect off the parabolic mirror toward an object attached to the igniter. So something here that's very flammable, right? Because the igniter is located at the focus of the parabola, the reflected rays of the sun bouncing off of the parabola here cause the object to burn in seconds. Use the dimensions provided in the figure to determine the depth of the fire starter. So I don't know if any of you have experimented setting a leaf on fire with like a magnifying glass, but magnifying glasses are designed by having kind of a parabolic shaped lens, which allows it to magnify what you're looking at, but it also can magnify the rays of the sun, and a parabola is the reason that works the way it does. It's also how our eyes work. Okay, let's go ahead and figure out what we've got here. So we know the width is 4.5. We know the depth is what we're trying to find. So what we're looking for. Use to find the depth, yeah. So then the distance to the igniter is 1.7 inches. All right, so that's our p value right there, right? And then that gives us a point here. If this is at 0, 0, we would have a point here at negative 2.25 comma, I'm going to call it d for depth, but I guess it's y, so maybe we shouldn't go changing our variable. So 2.25 is half of 4.5, and depth, just leave that at y. Okay, so that gives us this formula, again, facing upward, vertex at 0, 0. That means we can just use our basic thing here. So it's a y. Okay, so let's plug in one of our x's. So 2.25 squared equals 4 times 1.7 y. So then to find y, we're going to throw this in a calculator. 2.25 squared divided by 4 times 1.7. And what do I get? Actually, I have a paper right here that I can look it up on instead of grabbing my calculator. Now, what would have been faster, finding the page I wrote down or getting out my calculator? Either way, took a second, sorry. So when I plug that in, I get 0.74448 inches. I want to just approximate that and say, you know, that's about 3/4 of an inch. Maybe help you visualize that a little bit on how that would work. But here's our more exact answer. All right, we're all done with section 5.3.